to probability. So let's get started now. So what does probability mean? At the most basic level, this unit is on probability. And when we calculate the probability of an event occurring, we're calculating the likelihood or the possibility of that event taking place. So we're taking something which is uncertain, and we're calculating what is the likelihood of that event occurring. So basically, another way of saying it is we're giving it a number that predicts how likely it is to occur. And so the main formula, basically the most important formula in the whole of probability is this one over here. And it says for some event A, okay, some event or some experiment, what is the probability of the event A happening? And all we need to do is for this experiment, we say, well, how many possible outcomes are there for the experiment? So that's the denominator. How many possible outcomes are there? And then for the thing that you're calculating the probability of, the event A, how many of those outcomes are favorable for event A? So the whole of probability is basically based around this formula. And I'm going to do a question now in a moment where you get a sense of how this works. But when you calculate the probability of something, it can only be between 0 and 1, or on the percentage scale from 0% up to 100%. Probability doesn't exist outside of that range. 100% is certain, or 1 is certain, and impossible is 0. If there's an even chance, it'll be halfway along, or we say a 0.5% chance. And so we call this the probability scale. Okay. Just want to do a quick check. Give me a thumbs up if you've seen that basic idea before. Give me a thumbs down if this formula is completely new to you. Okay, so this is sort of, we get introduced to this for the very first time, normally sort of grade 9 or grade 10, but I see a couple of students haven't seen it before. So just remember this formula on the top. If you are working out the probability of an event A, the notation we use is P of A. And then the formula is, in this experiment that you're running, how many possible outcomes are there on the bottom, and how many favorable outcomes on the top? Okay, quite a few students haven't seen that before. Okay, well, let's go to a question where we can almost see this thing in action. Okay, so here is an example of a calculation involving probability. And what is the experiment? Okay, so the experiment is throwing this 6-sided dice. Okay, so that's the experiment. Now, it is asking us, what is the probability that the score is a factor of 6? Now, in order to calculate that, we need to use the probability formula that we saw above. So what is, and we'd say, how many possible outcomes are there for throwing a dice? And so if you think about a dice, there's 1, 2, 3, 4, 5, 6. So there are 6 possible outcomes. And the favorable outcome would be when the score is a factor of 6. Now, how many of those 6 items are going to be a factor of 6? Well, 1 is going to be a factor of 6. 2 is a factor of 6. 3 is a factor of 6. Okay. And 6 is a factor of 6. Okay. So if you think about that, there were 6 possible outcomes, and 4 of them would be a factor of 6. So the language of probability, we would say that the probability is 4 out of 6. Or in another thing, it would be written as 2 thirds. Okay, now, if I ask you to choose an option for the right answer, what are you guys going to choose? Okay, so you would choose option C. Okay, now I'm going to change the question a little bit in a moment because I can see a lot of you aren't familiar with how this works yet. So in the language of probability, if I said to you, how many items? So how many items? What is the n of the set? Let's call this. Okay, let's actually go with some naming conventions. If we talk about all possible outcomes for a dice, we call that, for any experiment, we call that the sample space. And so using set notation, we would say that for throwing a dice, there are 6 possible items. And so we'd say then that the number of items in S is 6. Okay. Then the other thing that, if we were using full probability notation, if I said to you, what is the size, what is in the set, things that are factors of 6. So I'm going to call that set F. That set, the set F, is the set of all items that are a factor of 6. So we would say in F, we would have the items 1, 2, 3, and 6, because all those items are factors of 6. If we then go, what is the n of F? Now, in statistics and probability, the n just means how many items are there in the set. And it would be 4. And so that's where the 4 and the 6 actually come from, in the sense that you count how many items are favorable for the question. There were 4, and you count how many items there were in total, and then you can do that calculation. Can I just have a quick, again, thumbs up, thumbs down check? Thumbs up if you're understanding what I'm saying. Thumbs down if you feel a bit confused. Okay, so everyone's still a little bit, we're getting there. Let me ask you another question then. I'm going to use the same options here, but I'm going to change the question. I'm going to say, what is the probability of, so if you're throwing a dice, what is the probability of getting a prime number? So a prime number. And I want you to think about what we've just done now. And I want you to choose the option that you think is the right answer. So what is the probability that the score is a prime number? Now, if you're rolling a dice, will the number of possible outcomes change? Will the number of favorable outcomes change? So remember our formula from the very beginning. On the bottom, we have all possible outcomes. And on the top, we have favorable outcomes, and it means favorable in relation to the question. So a favorable outcome would be the prime numbers. Okay, well, let's think about this. A dice will still only have 6 possible outcomes. So this is still going to be 6. But what does it mean to be a favorable outcome if I'm looking for prime numbers? Well, I know that 2 is a prime number. I know that 3 is a prime number. And I know that 5 is a prime number. Now, 4 is not prime, 6 is not prime, 1 is not prime. So how many outcomes are favorable for this question? It's just going to be 3 out of 6. which is going to be B. Okay. So I want to quickly go through some vocabulary, and then we're going to carry on practicing this idea. If we talk about calculating probability, we have this one formula that we really need to get used to, which I was just modeling for you now. The words that we use, a sample space of an experiment is the set of all possible outcomes. So in this case, the sample space was the numbers 1 to 6. But if it was a coin, the sample space would have probably been a heads and a tails. If it was a different size dice, the number of possible outcomes for this event we're measuring will change depending on the question. An outcome is a single observation of an experiment. So in this case, it's whatever the dice would land on. And then the event is a set of outcomes from an experiment. So the event in this case was a prime number, or earlier on it was a factor of 6. We also know that probability is calculated between 0 and 1, and it says how likely it is to occur. So 3 out of 6 is the fraction way of writing that. But in terms of percentage, there's a 50% chance that when you throw a dice, you'll get a prime number. So we say it's even. And then relative frequency is just kind of what we call experimental probability. So if you had to throw the dice several times and you would see how many times something came up, that would be the relative frequency calculation. Okay, but what I think we need is more examples to really get us going. So let's go straight to example number 2. So example number 2 is a spinner in the shape of a pentagon with a toothpick pushed through its center. And there are 5 triangles numbered from 1 to 5. The spinner will spin until it lands on one of the 5 edges of the pentagon. What is the probability that the number it lands on is odd? And I want you to try and calculate what is the probability that the number it lands on is odd. Okay, so I see some answers coming through. Now, in probability notation, I'm writing it like the official way. I'm saying that if a number is odd, okay, then it would be either 1, 3, or 5. And if a number is S, it would either be 1, 2, 3, 4, or 5. The S is the sample space. O is the event of throwing an odd number. So using the formula we did at the beginning, the number of possible outcomes is just the size of S, which is just the N of S, and that would be 5. And then how many outcomes are there, or favorable outcomes are there? There's O. Guys, I just want to close my door quickly. I'll be back in a second. Okay. There we go. So what we have is we have that as 3 over 5. And so the answer should be D. Thumbs up if you got that right. Thumbs down if you're feeling a bit lost. Let's have a quick look there. Okay. Awesome. Are there any questions before I move on, everyone? Are there any questions about my fancy set notation? So what we have here, like, do you understand what I mean by odd is 1, 3, and 5, S is 1, 2, 3, 4, and 5? Back in a second. Okay, cool. Let's move on to the next one. Go for that. See if you can do that one. Yeah. Okay. Cool. How's it going? Sorry, guys. Someone was using their weed eater, so I had to go.
Bad timing.
Yeah. Okay, so we have an 8-sided dice. So the sample space would just be those items. And we want a prime number. So the primes would be 2, 3, 5, and 7. And so what is the probability that has a prime number? Well, the probability I'll use is going to be the number of items in the sample space. So that'll be 8. And the number of items in the prime. So it's 4 over 8. And 4 over 8 is the same as a half. How's that? Awesome. So I see lots of people who got C there. Cool. All right. I think we can move on to the next question. Everyone's looking pretty good. Let's do this one. Okay. So you are given the word Mississippi, and the letters of that are basically each of them letters on a separate piece of paper put into the hat, and you choose a letter. What is the probability it is an I? I want you to calculate that for me. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the N of S is 11. There's 11 items in the sample space. How many ones are favorable? Basically, how many I's are there? 1, 2, 3, 4. I count 1, 2, 3, 4 I's. And so what does that mean about my probability calculation? Anybody else? Okay, so it is going to be 4 out of 11. That's it. Awesome.
Great going, guys.
Well done, everyone. Okay, I'm taking it up a little bit now, and we might need to get some help from the class. You've now got a pack of cards. So the sets that are involved are a bit bigger now. There are 52 cards in a playing pack. There are 4 queens and 4 kings, 1 for each suite. What is the probability that the card chosen is a queen or a king? Go for it.
Keep going, guys. Looking great.
Okay. There we go. Okay, who wants to come online and explain how they did this one? Who feels like volunteering their ideas before I give the answer away? I'm curious to know. So I see William, Nolutando, Rafiwe, have all got answers locked in. Who wants to explain their answer? How did you do it? Because I don't see any 52s. So I'm wondering how you made the jump from that. Okay, William. Yeah, let's go to you. How did you make that connection, William? What was your answer?
So my answer was B, 2 over 13. Because they told us that they gave us, there are 4 queens and there's 4 kings. And in the question they asked us the probability of choosing a queen or a king. So that basically is, I learned in school that means addition, the king and the queen all together. And I had over 52, which gave me 2 over 13.
Okay, so you took 8 on the top there and 52, and then you, oh, okay, so then an equivalent fraction would be 2 over 13.
Yes, sir.
Perfect. I agree with you. So B is the answer. Yeah. Awesome. Okay, so I just want to, again, check that all of the things we've done so far come back to the probability formula, which is the probability of some event is the number of possible outcomes. So how many things are possible over the number of favorable outcomes, which depends on whatever that event is that's being asked about. And so that we're always going to come back to that calculation. Now, the events might become more complicated. And so we knowing how to count these gets more interesting, but we will always come back to this formula. Now, before I go on to the next type of question, I want to know what are some of the techniques that you've learned about for more complicated questions for counting the number of possible outcomes. But has anybody got some ideas about like the techniques that they've seen in earlier grades? Because the questions now are going to get a little bit more, there's going to be more parts to them, but I just want to see what techniques you've learned. Has anybody heard of something called a Venn diagram? Or has somebody heard of it? What else? What other techniques? A tree diagram or a table diagram? So those are 3 possible techniques that could be useful. The 2 circles together. Yes, Komutsile. So one way of counting, so yeah, there we go, Emikle. Yeah, so we have things called Venn diagrams. We also have things called tree diagrams that help us keep track of how many possible outcomes. And we also have things called table diagrams or tables that help us keep track of different outcomes. Okay, so I just wanted to bring that up. And you're right, we have things called identities. And identities are just relationships between sets and probabilities, which we'll talk about a little bit later in this course. But let's see what other tools we can use here. So here is a question which it's a little bit harder to keep track of how many possible outcomes there are. And so I want to ask you guys, what type of diagram do you think would be helpful for this particular question? I don't want the answer, but I just want to know what type of diagram or technique do you think would be helpful to help us calculate the formula, favorable outcomes over all the possible ones. Ooh. Which is what we're going to have to do. So I see lots of you are saying tree diagrams. Okay. So when we draw a tree diagram, what happens is a tree diagram is used when there are multiple events, compound events, or multiple repetitions. In this case, the coin is tossed 3 times. And when we toss a coin, there are 2 possibilities. There are heads and tails. Now that would be for a first toss. But now what happens is we extend this diagram for a second toss. And this shows us the possibilities if we throw the coin a second time. Now, I want you to think about if you had to extend this diagram to a third row or third line, could you use it to help you calculate the probability of obtaining 1 head and 2 tails? So take a moment now to think about, can you extend this tree diagram? And this is a very basic tree diagram. It's just showing you all the possible outcomes, and you need to extend it. And then can you try and answer the question? So you toss a coin 3 times. What's the probability of obtaining 1 head and 2 tails? Well, how many possible outcomes are there? 1, 2, 3, 4, 5, 6, 7, 8. So I have, if I look, one possibility is heads, heads, heads. Another possibility is tails, tails, tails. Another possibility is heads, heads, tails. But basically, each one of these final things is one of the possible ways it could fall. And so in total, there are 8 possibilities. Now, how many of those possibilities are going to be favorable based on the event question? And the event question is 1 head and 2 tails. So 1 head and 2 tails would not be this one. It's not that one. 1 head and 2 tails, not that one. It is this one. It's not this one. It is that one. 2 tails, and it is that one, and it's not that one. So if I look at my drawing, I see that heads, tails, tails is one option. Tails, heads, tails is another option. And tails, tails, heads is another option. And so the correct answer is going to be 3 out of 8, which is question C. So give me a quick feedback thing. Thumbs up if you understand that. Thumbs down if you feel like I need to go through a very detailed example of that again. Okay, awesome. Okay, so we definitely need to do another one of these, which we'll do after the break. But on the whole, I think the basic idea of a tree diagram has been laid down. So let's stand up for a second and let's stretch because we've been working hard. So if you could turn your cameras on, ladies and gentlemen, and then if you could stretch it out. And Lebo, if you could please encourage our students to stretch out, and I'm going to stretch out with them.
Please join in, guys. Give your mind a break.
Give your mind a break. We're working hard. Stretch it out.
Get a bit of a boost before the last half.
Exactly.
Don't be shy to turn your cameras on. We love to see your faces.
Come on, guys. We want to see your awesome
shout out
faces.
Imihle.
There we go. Stretch it out, guys. Oh, double click. hear that. And stretch your neck out. Oh, that feels good. You can do it, Teddy. You can do it. Come on, William. Stretch it out, guys.
Yes, Lysanda, shout out.
There we go.
Shout out to Ari. There we go.
There we go. You see, now you feel like part of the team. Woohoo!
A team that stretches together wins together.
Exactly. Okay, here's your brain break for today. A train is traveling 300, a 300-foot train is traveling 300 foot per minute and must travel through a tunnel, long tunnel. How long will it take to travel through the tunnel? Okay, that is the question. So a 300-foot train is traveling 300 foot per minute and must travel through a 300-foot long tunnel. How long will it take to travel through the tunnel? Aha, Kumutsile. Lock your answers in, guys. Lock your answers. A minute. Let's go. Let's go. Some people think it's a minute so far. It could be right. I will reveal all in a moment. Aha. Are there any dissenting voices? So a 300-foot train is traveling 300 feet per minute, and it must travel through a 300-foot long tunnel. How long will it take? Okay, it's time to reveal the answer. Is it going to be a minute? So it takes 2 minutes. Why does it take 2 minutes, everyone? It takes 2 minutes because the front of the train takes 1 minute, and the rest of the train will take 2 minutes. Well, the rest of the train will get through it after another minute. And so in total, it will take 2 minutes to clear the tunnel. So the first minute will be getting the front of the train through. The second minute will be about getting the rest of the train through. And so the answer will be 2 minutes. Okay. So that was an interesting one. It caught quite a few of you. Just think about it. Yeah, think about that a bit further. But yeah, I see iPhone has got it. Does that make sense to you? Give a thumbs up if you get why it takes 2 minutes. Asimak says, oh. Okay. So that is the brain break for today. And I think we did pretty well with the brain break. We managed to stump quite a few students today, which I try my best to find some interesting questions for you. Okay, let's go back to the probability that we were doing. So far in the lesson, we've learned about this probability kind of equation that we use every time. And then we've learned about different ways of knowing the possible outcomes and the favorable outcomes. And we've just seen a tree diagram for the first time. So I want to ask you another tree diagram question here. Well, maybe it's not a tree diagram. It depends if you want to use that, but you maybe can see. It says, a fair 6-sided dice and a fair coin are thrown together. What is the probability of getting a multiple of 3 on the dice and a head on the coin? So this event is what we call a compound event because there's 2 things that are happening. You are throwing a dice and you are throwing a fair coin, and they're thrown together at the same time. The event that we are interested in getting is a multiple of 3 on the dice and a head on the coin. Can you use what we've learned so far in the lesson to work out the probability of that occurring? I'll give you a little hint. So for me, all the possible outcomes, how many possible outcomes are there? Because that's what I always think about. And for me, there are 12 possible outcomes because there's heads 1, heads 2, heads 3, and so on. So all of the end of the tree diagram, there's 6 options here and 6 options on the bottom. So in total, the number of possible outcomes is going to be 12. How many of those outcomes are going to be favorable when you consider the event we're thinking of? So if we are a multiple of 3 and a head on the coin, so I can only be in this top half. I can't be in the bottom half because the bottom half would have a tail. So heads is here. And which ones are multiples of 3? So a multiple of 3 is 3. So that option, heads and 3, or you could have heads and 6. So in total, we should have, dice here on the coin, we should have 2 out of 12. Now, is there a 2 out of 12 there? No, but there is an equivalent fraction, which is going to be 1/6. And so the correct option would be 1/6. So a tree diagram can be very useful in certain situations where the events either happen multiple times or they're a compound event, where they're like a combination of things. And it just gives us a way to count how many possible ones, and then we count how many are favorable in relation to the question that's being asked of us. And so the correct answer would be A. Okay. Are there any questions, ladies and gentlemen? Are there any questions? Okay. All right. Well, then I'm going to move. Oh, Asimak, let's go to you. Yeah. Hey, how's it going?
Hi, sir.
Hey.
I wanted to ask, I did it differently and I don't know if it's gonna work every time. Like I calculated the probability of the 2 separate things happening, and then I multiplied the fractions that I got together.
That will work as long as they're independent events. We're going to get to that in the later lessons, and there's nothing wrong with that, right? It's just a matter of, at this stage, I was wanting to show kind of how to keep track of the number of outcomes using a technique. But you're completely fine. As long as the events are independent, you could multiply them like that. Yeah.
Okay. Thank you, sir.
Pleasure. Okay. Let us answer this question. So a 50-cent coin and a 10-cent coin are tossed together. Which of the arrows, A, B, C, or D, shows the position on the probability line for the event both coins land tails up? So you're thinking about the event, both coins land tails up. Which arrow points to the correct probability for that? You may not need a tree diagram. But you could use a tree diagram. It depends on, or you could write out the options. So you've got 2 coins that are being tossed. So coin 1 would be heads and tails. So coin 1. And then coin 2 would also be heads, tails, and heads, tails. How many options are there? There should be, for me, there should be 4 options. You could have heads, 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 tails, tails, heads, tails, tails. So there are 4 possible ways that the coins could land. You're interested in both coins landing tails up. So tails up would be just one of the options. So it would be this one here. So it would be 1 out of 4. And which of those is 1 out of 4? It's going to be option B, which is here. Okay. How's everyone? I see most of there were a few questions here. Are there any questions about how I got that? I see a couple of you got D, but remember, we were calculating when it lands both tails up. So, okay. Can I repeat that? Okay. So, if you think of the question, how many ways are there for 2 coins to land? There's heads, heads. So that's like the first option. Option 1, there's heads, tails. There's tails, heads. And there's tails, tails. So how many ticks are there? There's 4 possible ways. That's why there's a 4 here. In this question, they've said, what is the probability for the event that both coins land tails up? So basically they're saying, what is the probability of having tails and tails? And only one of the branches has tails, tails, which is this one here. And so that's why it's going to be 1 out of 4. Now, 1 out of 4 is just the option B on the probability scale. Okay. So again, we always come back to how many possible options are there? And we need a way of counting those or visualizing it. In this case, we used the tree diagram, but there are other ways of doing it. And then how many options were favorable for the question? And then we went from there. Okay. Let's end the lesson with 2 more questions. We'll leave relative frequency for now. And we'll leave that one for now. We'll leave that one out for now. Let me go to, where's the one here? Okay, let's do this one. Try this one. So there are 12 red roses, 5 yellow roses, and 3 white roses in a vase. Felix takes 1 rose at random. What is the probability that it is yellow or white?
Mr. Ace?
Yeah.
Can you please check out Nantawego's question in the chat?
Okay. So, Nontobeko, you do go to the second one. Nowazi, you do go to the, you do look at the second row for the variation, but it is possible to get heads, heads, tails, tails. I'm going to try and come back to that later in the lesson. I'm just going to focus on this one for now. Let's just make sure, let's finish with these 2 foundational questions. We'll go from there. Okay, so how many possible options are there? 12 red, 5 yellow, and 3 white. So in total, there should be 20 possible different things that can happen. And we want to know what is the probability it's yellow or white. So there are 5 yellow roses and 3 white roses, which means there's 8 favorable outcomes. So 8 out of 20. And then I don't see 8 out of 20 here, but what I do see is that that is equivalent to 2 out of 5. And so that should be that one there.